Hello everyone, this is lecture 23 of the subject analog circuits. In this class I am going to discuss differential amplifier with active load, multistage amplifier and the concept of stability. So, starting with the differential amplifier with active load. So, in the last class, that is lecture 22, I had already discussed differential amplifier, about the basics of differential amplifier with passive load. So, in this class firstly I am going to discuss the differential amplifier with active load. So, before starting the topic, let us quickly review this differential amplifier DA. So, basically the main advantage of differential amplifier DA, that is differential amplifier noise reduction. The effect of noise is lesser in case of differential amplifier, because it amplifies the difference between two signals, and if any interference signal, any noise signal is added to the circuit. So, it does not allow that interference signal, noise signal to propagate further, fine. That is the main advantage of DA, and also it removes the requirement of the bypass and coupling capacitor that saves the chip area, fine. That is the main advantage of differential amplifier. So, in the last class we have we had designed the differential amplifier with resistors, but the issue with the resistor is that the resistor occupies more area in chip, in integrated circuits. So, we want to replace that resistor. So, in differential amplifier with active load, what we have done, we have replaced those resistors with transistors. There is a passive load, that is the resistive load. Here the load is the transistor, and this load is current mirror, that load is Q3 and Q4. Now, if you compare this circuit to the previous circuit that you have studied in the last class, just those two resistors RD are replaced with this current mirror, and of course, this current mirror is made up of transistors. That is why we are saying it as differential amplifier with active load. I have discussed this current mirror in lecture 20 and lecture 21, you can refer those lectures. So, you can see that this Q3 and Q4, it forms the basic current mirror, using PMOS transistor, fine. You can see that the source of the Q3 and Q4 transistors are connected, shorted, and the gate are shorted, fine, and the Q3 is the diode connected. So, this Q3 and Q4 is the current mirror, and this is the basic current mirror using MOSFET. And this Q1 and Q2, transistors are the input transistors. These are the input transistors. Why we are saying it input transistors? Because we are applying the input signal at the gate of Q1 and Q2, and this current source I, it is used for the biasing purpose, to make sure that this Q1, Q2, Q3, Q4 it should be in saturation region, because this is MOSFET, fine. So, this is your differential amplifier with active load. Again there are different cases, we can apply the input signal as a differential input or single ended input. Like in the last class we had seen that we have applied the input signal at both the transistor and at the single transistors also, but the gate of the another transistor is grounded. So, ultimately that signal is the differential input, that should be differential, that is why it is called differential amplifier. And as far as output is concerned, so we take the output in single ended manner, we can take the output in differential manner. So, if we are taking the output only from one of the drain of the transistors, like in this circuit you can see that we are taking the output from the drain of the Q2 transistor, then it is called single ended output, and if we take the output between the drain of two transistors Q1 and Q2, that is called the differential output, and that differential output is having the advantages like gain is higher, CMRR is higher, but in many applications we require single ended output. So, we need to understand both, fine. Now, for the same circuit, if we understand it at equilibrium position, at equilibrium condition, it means that if the gate of Q1 and Q2 are grounded. So, what will happen? Q1 and Q2 transistors are in saturation region. So, the equal current will flow through Q1 and Q2 transistor. The total current is I, that is the bias current. So, I by 2 current will flow through Q1 transistor. Now, you can see that Q3 and Q4 are current mirror. So, this I by 2 will copy to the Q4 transistor, and the current flowing through Q1 transistor is I by 2 and Q2 transistor is I by 2. So, ultimately what we are getting at the output, the current is 0. You can see that from Q2 transistor I by 2 current is flowing, and from Q4 transistor I by 2 is flowing. So, from the output, at the output we are not getting any current. When this circuit is at equilibrium, obviously assuming the perfect matching. Perfect matching means the Q1 and Q2 are perfectly matched, the threshold voltage mu and Cux are same for Q1 and Q2 transistors, fine. Similarly, again for that differential amplifier with active load, considering that the circuit with the differential input signal applied and neglecting the R naught. For the time being we are neglecting this R naught, but see in IC designing we cannot neglect R naught, but for just simplicity we have not considered R naught here, fine. But in IC designing we cannot neglect it, but in discrete circuit we can neglect this R naught. Now, see again the input signal, it is applied in the differential in the complementary manner. In fact, complementary manner means at the Q1 gate of the Q1 plus VID by 2 and at the gate of Q2 minus VID by 2. Now, this is the small signal operation. In fact, you can see that the DC sources are removed, DC voltage source and DC current sources are removed, right. So, this is the small signal operation. So, if the Q1 transistor, current flowing through Q1 transistor is I, that is current flowing through Q3 transistor also, right, and Q3 and Q4 it forms a current mirror. So, the current flowing through Q4 transistor, it will also be I. From the circuit you can see that if the current flowing through Q1 transistor is I, then through Q2 transistor the same current will flow, but in opposite direction, fine. So, point is that the same current is flowing through Q2 transistor, that is I, but in opposite direction. So, you can see that at the output what will be the current? I current is coming from Q4, I current is coming from Q2. So, these two currents will be added. So, at the output we are getting total current 2I, and this 2I we are getting just because of the current mirror operation, So, for this circuit we can calculate transconductance, we can calculate the output resistance and differential gain. So, the transconductance GM of this differential amplifier with active load is GM. This GM is the transconductance of the individual transistor Q1 and Q2, those are the input transistors. And again we can calculate the output resistance R naught. So, in lecture 21 I had discussed the procedure how we can calculate the output resistance of any circuit. There I had given an example of Wilson current mirror, there we had calculated the output resistance of Wilson current mirror. Similarly, following the same procedure you can calculate the output resistance of this differential amplifier with active load. For that again connect a voltage source at the node at which we need to calculate the resistance, and it means that we are taking the output from the drain of Q2 and Q4, then at the drain of Q2 and Q4 we will connect a voltage source Vx. We will assume that due to Vx current flowing is Ix, then at that node we can calculate Vx upon Ix, and this will be your output resistance R out just by doing some network analysis, fine. So, after calculation we get RO2 parallel to RO4. What is RO2? RO2 is the output resistance of Q2 transistor, RO4 is the output resistance of Q4 transistor. So, we can see that we are taking the output from the drain of Q2 and Q4. So, what is the output resistance at the drain of Q2 and Q4? That is the parallel combination of the output resistance of Q2 transistor and Q4 transistor. You can derive it, just follow the procedure which I had discussed in lecture 21, fine. So, after it we can calculate the differential gain, that is V naught upon VID. V naught is the output voltage, VID is the input differential voltage, that is GM into R naught. GM is the transconductance of the differential amplifier, R naught is the output resistance of the differential amplifier, and the output resistance is RO2 parallel to RO4. So, the gain is GM into RO2 parallel to RO4. And if we consider the case if RO2 equal to RO4 equal to R naught, then what will be the differential gain? It will be 1 by 2 GM R naught. This GM R naught can be written as A naught. This GM R naught, it can be written as A naught. This A naught is called intrinsic gain of the MOSFET. GM is the transconductance of the MOSFET. R naught is the output resistance of the MOSFET. So, these are the results of the differential amplifier with active load. And again I repeat that what are the advantages of this differential amplifier with active load? There are two major advantages of differential amplifier with active load. The first advantage is the gain is higher, the voltage gain is higher, and the second advantage is area is reduced, right. So, if we are replacing those two resistors RD with current mirror load, that is the active load, then the gain we will get higher gain, the first thing, right. You can see that we are getting the gain, that is here we are getting the gain, that is GM into RO2 parallel to RO4, right. So, in active load case we are getting higher gain and area is less because there is no resistor in the circuit. These are the two main advantages of differential amplifier with active load. Now, coming to the next topic, that is the multi-stage amplifier. So, up to now we have studied common emitter amplifier, common source amplifier, that is a single stage configuration, and after that differential amplifier. Multi-stage means when we connect more than one amplifier in cascade. For example, this is the first stage and suppose that the voltage gain of the first stage is AV1 and the input of this the input signal which is applied at the first stage, that is V, and output is VO1. Now, the output of the first stage is connected to the input of second stage, and the output of the second stage is VO2 and the gain of the second stage is AV2. Similarly, we can design it up to nth stage, right, and the final output is V naught. This is the structure of the multi-stage amplifier in which more than one stages are connected in cascade. Now, obviously, the question arises that why we need to connect these stages, these amplifiers in cascade. The reason is that with the help of single stage we cannot get enough gain. In some applications the higher gain is required. In communication system, in many modulators, gain of 70 dB, 80 dB, 100 dB is required, and that cannot be achieved with the help of single stage amplifier. So, we cascade different stages to get the higher gain. Now, if we cascade the amplifiers like this, then what will be the gain of the overall structure? The gain of the overall structure, it will be the gain of the voltage gain of the first stage into voltage gain of the second stage into voltage gain of the third stage, similarly the voltage gain of the nth stage. So, it means that when we cascade the amplifiers, then the gain increases. So, it means that if we are considering two stage amplifier, two stage means we are connecting two amplifiers in cascade, amplifier 1 and amplifier 2. We are applying the input signal at the input of amplifier 1 and the output is connected to the amplifier 2, input of the amplifier 2, and the final output is V naught. and if the gain of amplifier 1 is AV1, gain of amplifier 2 is AV2. So, the overall gain of this two stage amplifier will be V naught upon V in is equal to AV1 into AV2. So, we get higher gain. So, the purpose of designing the multi-stage amplifier is to get the higher gain, because in some application it is required, fine. So, similarly we can design 3 stage, 4 stage amplifiers to get the higher gain. Now, the issue is that when we design the multi-stage amplifiers like 2 stage, 3 stage, 4 stage amplifiers, then the number of nodes increases. So, number of poles and zeros also increases in multi-stage amplifiers. Due to those poles and zeros, the circuit becomes unstabilized. Means when we go for multi-stage amplifier like 2 stage, 3 stage, 4 stage, so we need to check the stability of the circuit, because in higher stages, in multi stages, the number of poles and zeros increases. So, it may happen that some zero is there in the right half plane, some pole may come in the right half plane. If it is happening, then your circuit, then your amplifier will not be stable, and if your amplifier is not stable, then what is the use of that amplifier? There is no use of such amplifier if we are not getting the stable output. We will get distortion, we cannot control the output. So, we need to stabilize that amplifier. For that we use frequency compensation techniques that I will discuss in the next class. Now, before discussing that frequency compensation technique, let us review the stability concept. How we determine the stability, how we say that whether this amplifier is stable or not, how we will conclude that. For that, we need to understand the concept of stability. So, to determine that whether that amplifier is stable or not, let us consider 2 stage amplifier or 3 stage amplifier. For that, calculate the transfer function of that amplifier. You can calculate it. That transfer function is V naught S upon V in S. We can calculate V naught S upon V in S, transfer function of that amplifier. And after calculating, just draw the gain response and phase response of this transfer function. Gain response means the voltage gain in dB, that is at y axis, and frequency is at x axis. This is the first graph, and this is called your gain plot. Similarly, for this transfer function, we will draw the phase plot. The phase plot is the graph between, that is the graph between phase versus frequency, right. Let us consider that if we are getting like graph like this in gain plot, and this is your 0 dB line, 0 dB line. 0 dB means the frequency at which the gain is 0 dB. 0 dB gain means the gain is 1, the gain is 1. If we convert that 1, that is in ratio in dB, that will be 20 log 1, that is 0 dB, fine. So, this frequency is called omega g, that is called gain crossover frequency. Gain crossover frequency is the frequency at which the gain is unity, gain is 1, that 1 is in ratio, but in dB it is 0 dB, fine. Similarly, we will draw the phase plot for this transfer function. It is your 0 degree, and suppose that this phase plot is like this. I am randomly drawing it just to make you understand that how we calculate the stability, how we determine whether the amplifier is stable or not, fine. And we draw a horizontal line from minus 180 degree phase angle, right. So, this is your minus 180 degree line, for example, and here it is crossing this minus 180 degree. So, the phase plot, the frequency at which the phase plot is crossing minus 180 degree line, that frequency is called omega p, that is called phase crossover frequency, that is called phase crossover frequency. What is gain crossover frequency? Gain crossover frequency is the frequency at which the gain is unity. Phase crossover frequency is the frequency at which the phase is minus 180 degree. Fine. Now, to calculate the stability, we calculate the phase margin. To calculate the phase margin, what we do? We draw a vertical line from the gain crossover frequency, that I am drawing it with blue color. Obviously, this vertical line which is drawn from gain crossover frequency, it will cut the phase plot at particular angle. Suppose that angle, you can see that this angle will be, let us say it is minus 200 degree, then the phase margin it will be equal to 180 degree plus that angle at which this vertical line is cutting the phase plot, and the angle at which this vertical line is cutting the phase plot is minus 200 degree. So, the phase margin it will be 180 degree minus 200, it will be minus 20 degree. So, the phase margin is negative. If the phase margin is negative, then the circuit, the amplifier will be unstable. Similarly, we can calculate the gain margin. In gain margin, what we do? We draw a vertical line from the phase plot at which the phase plot is crossing the minus 180 degree line, right, and from here we can calculate the gain margin. Fine. For the amplifier to be stable, the gain margin and phase margin it should be positive. For amplifier to be stable, for stability, the gain margin and the phase margin it should be positive. If any one of it is negative, then the amplifier will be unstable. Fine. So, we want to stabilize the amplifier, only then we can use that amplifier. So, to check the stability, we will follow this procedure. This is called your Bode plot. In Bode plot, there are two plots. One is your gain plot, another one is your phase plot. This is called your phase plot. So, here you can see that your amplifier is unstable because your omega p is greater than omega g. Phase crossover frequency is greater than omega g. Not, it is not correct actually, it is not correct. From this plot we can see that your omega g is greater than omega p, right. You can see that this is your phase crossover frequency, this is your gain crossover frequency, and gain crossover frequency it is greater than phase crossover frequency, and whenever it will happen, whenever your omega g will be greater than omega p, in that case your phase margin will always be negative, and if the phase margin is negative, then the circuit will be unstable. Let us consider a plot for a stable system, for a stable amplifier. Fine. Again I am drawing the gain versus frequency plot and phase versus frequency plot. That gain is in dB. This is your gain plot. This frequency is your gain crossover frequency at which it is crossing the 0 dB line, that is equivalent to gain equal to 1, and this is 0 degree, and this is your phase plot, right, and let us say this is minus 180 degree line. Fine. Now, again we are going to calculate the phase margin. To calculate the phase margin, what we do? We draw a vertical line from the gain crossover frequency, and of course it will cut the phase plot at a particular angle, and this angle, now this time let us say it is minus 135 degree, then what will be the phase margin? The phase margin will be 180 degree plus that angle is minus 135 degree. So, the phase margin is 45 degree. Now, it is positive. So, in this case the phase margin is positive. So, this amplifier is stable. Now, what is the phase crossover frequency? Phase crossover frequency is the frequency at which the phase plot is crossing the minus 180 degree line, that is omega p. So, from this plot you can see that your omega g is less than omega p, omega g is less than omega p, gain crossover frequency is less than phase crossover frequency. So, whenever it happens, then your phase margin will be positive, and when you calculate the gain margin, it will also be positive in this case, right. So, the point is that if we are designing any multi-stage amplifier, so we need to check the stability, because there are comparable poles and zeros and it can degrade the stability. Your phase margin may be positive, if it is you are getting plus 2 degree, plus 3 degree, it is positive, but that is not the sufficient phase margin. The optimum value of the phase margin is approximately 60 degree. So, we want sufficient and optimum phase margin, right, for better stability. So, the point is that if we are designing this multi-stage amplifier, so calculate this transfer function, draw the gain and phase plot and calculate the phase margin, check that whether it is stable or not. If it is stable, then in that case also we should get the sufficient phase margin. It is not like that if we are getting 2 degree, 3 degree phase margin, that is positive, but that is not enough, that is not enough. In that case also we will get ringing at the output. To get the better output, the phase margin it should be at least 45 degree, 45 to 60 degree, 65 degree, that will be fine. So, let us consider the amplifier which is having this plot and the phase margin is minus 20 degree. This is not acceptable. We have to stabilize this amplifier. For that we will be using in the next class the frequency compensation technique. One of the frequency compensation technique is the Miller compensation to stabilize this amplifier to make the phase margin positive and sufficient. Fine. So, this is the concept of stability. Of course, this concept of stability, this gain response, phase response, it can be applied to single stage, but normally the stability issues mainly arises in multi-stage, in 2 stage, 3 stage and 4 stage. Fine. So, in this class I have discussed the differential amplifier with the active load, and after that I have given you a small overview of the multi-stage amplifier to get the higher gain, and after that concept of stability. In the next class I will discuss the designing of this multi-stage amplifier, designing of op-amp, and how we use this frequency compensation technique to stabilize the circuit, to stabilize the amplifier to get the sufficient and enough phase margin. Fine. This is the reference. Thank you.